Oh, you gotta.
Yeah,
Or the
those are real nice.
or the definition or something like where it's like it has to be exponential, and I forgot the other thing. I was taking notes, but in order for you to be able to.
Well, so for these first ones, I mean, it says to do it using the integral formula. But of course, what you could do is just look on that table in your book and just do it that way if you want.
Oh yeah, that's true.
Some of them aren't going to be on there, but most of them will be.
Like the one right here with the T, you have to. It says that if you do what the derivative of the.
Yeah. So you could do it that way. You could.
I'm sorry. Go ahead.
You could just do the e to the 4t and then take the derivative of that, and it's going to give you the same thing. It should give you the same thing.
You should.
Mm-hmm.
Let's do one of these in live. That way I can ask questions when I have a question.
All right. Let me get a new page here. All right, so you want to try one of these where you're actually doing the integral?
Yeah, let's try one.
All right, let's do this one then. So the t, e to the 4t, and we're trying to find the Laplace transformation of that. The formula for it is the integral from 0 to infinity of e to the negative st times the function, so t e to the 4t dt. So what's going to happen is that the t's are going to integrate out, and you're only going to be left with s's left over, which is why we call the Laplace transform a function of s. All right, so just to simplify down this integral, we have two e functions, which when we multiply those together, we're adding the exponents. So moving the t to the front, and then when I multiply those e's together, I have a negative st and a 4t. I think how I'm going to write it is 4 minus s all times t.
Okay.
I think the way that we wrote it out in the notes was just slightly different. We just factored a negative sign out.
Right.
So we might as well do that just to keep it consistent with the notes. So we would write this as negative s minus 4t, like that. And then we just do this integral. But unfortunately, to do this integral, we're going to have to do integration by parts.
Oh, okay, I see, yeah.
So we're going to let the u be t, the dv be that e thing, which means that we have to find the du and then the v. So du, just the derivative of the t, so just 1 dt. And then we have to be careful here. It's the antiderivative of this e, which is going to bring down the reciprocal of the coefficient on t. So it's going to bring down negative 1 over s minus 4, and then we get that same e value. Okay, and then we do the integration by parts. So it's u times v so the t times this awful-looking v minus the integral of this awful-looking v du, which is just going to be really the dv part. All right, so just copying it down. We still have that thing out in front. I'll just leave that alone. And then we just got to be careful here. So the double negatives is going to make this a positive. I can go ahead and bring out that constant, the 1 over s minus 4 part. And then we can do the antiderivative of that e that would be left over. that is going to bring down another one of these reciprocals, 1 over s minus 4, and then again leave that e value alone. Right, so the 1 over s minus 4 that was already there we brought out. The antiderivative of this e brings down another one of these. 1 over s minus 4 is a negative one. Okay, and now we still have to do the limits from 0 to infinity. So just copying it down one more time and cleaning it up just a little bit more. So we can combine those constants together to be a s minus 4 squared in the denominator there.
Okay.
All right, and then we're plugging infinity into both of these things. But keep in mind, we're plugging it into the t's. It has nothing to do with the s's. When I plug infinity into this first term, I'm going to have this t, which goes to infinity in the numerator. This e I would move to the bottom because of the negative sign, and then that's going to go to infinity. So really what we have is infinity over infinity, so we have to do L'Hopital's rule here. But when you take the derivative of t, you just get 1. When you take the derivative of this e, you're still going to have an e, so that first term's just going to go to 0. All right, so this is 0 for infinity. The second term, when I plug infinity into that, my denominator has the e in it, so it's going to go to infinity, which makes the whole thing go to 0. Minus plugging 0 into both of these things. When I plug 0 into the t for this first term, because of this t up top, it goes to 0. When I plug 0 into this, the e goes to 1, so we're just going to get that coefficient, that 1 over s minus 4 all squared. All right, that's a lot of ugly parentheses, but the whole point is that we just get this.
Right, and you can just look at the chart and get that.
We could have just looked at the chart. I mean, it would have been a little bit more than just looking at the chart. I don't have the chart like pulled up here, but I'm pretty sure that if you just have e to the 4t, the Laplace transform of that is 1 over s minus 4. Or maybe it's negative 1 over s minus 4, something like that. But this t out in front says to take the derivative of this. And then the derivative of that is how we get the squared there in the denominator.
Okay, so it's a little bit more than just looking at the chart, like you said. But...
yeah, only because of that t out in front. I don't remember. Maybe there is one that has the t's and then the e's on that chart. I should pull up the chart. I think one of the later homework questions has the chart. Yeah.
Oh, yeah.
Oh, yeah, look right down there. It is here. So, yeah, we could have just done the chart. Our n would have been 1, and then our a would have been 4, and we get 1 factorial over s minus a squared, which is exactly what we got. 1 over s minus 4 squared.
And then the, whatchamacallit, the restrictions or... not restrictions, but...
yeah, that's a good word for it. The restriction for s, yeah, it is important. So for this one, we got 1 over s minus 4 squared. And because of that s minus 4 in the denominator, that says that your s has to be greater than 4. You also get that from the table.
Are you just like solving it for like s? You're not solving it, but like...
you want to think of it more like you want your integral to exist. So if I go back to this, if my s was less than 4, I would get a negative value here, and that would mess everything up. Because when I plug infinity in for the exponent, if that's a negative exponent that's already negative, then it's going to be positive, which blows up to positive infinity instead of going to 0. That was a lot. Let me try to make it easier. For this part right here, the e to the negative s minus 4t. If I have, so let's see, if s is less than 4, then s minus 4 is a negative number, right? Which means that you're taking e to the, when you plug t to be infinity into this, you have the negative sign out in front. Your parentheses is also going to be a negative something, and then your t is going to be infinity. Which really means that you're taking e to the positive infinity power, which is going to make it blow up, which means that your integral wouldn't exist. So because of this, you have to have s minus 4 to always be positive, and the only way s minus 4 can always be positive is if s is greater than 4.
That makes sense.
Yeah, but yeah, you don't actually have to know why that's the case, because the table tells you what the restriction is. So for that one that we were looking at here, the table will tell you that the restriction has to be s is greater than that exponent for e.
Could we do this one?
Yeah, so this is more like the questions that you're going to see moving forward, especially when it comes to test type questions. So here we have a bunch of different functions that we're trying to take the Laplace transform of, and it's just like a linearity thing. You can break it up into all of the different ones individually. So really what we're trying to do is the Laplace transform. I'm just going to do capital L instead of that curvy L. So
yeah, my L's, the clause starts looking like 2, and I gotta be careful.
So we're going to do the Laplace of the first one minus the Laplace of t cubed plus the Laplace of 3t minus the Laplace of 9. And then even more that we can do is that we can take out all of those coefficients. So that first one, we can bring the 8 out. The second one, we're just kind of stuck with. The third one, we could bring a 3 out. And then that last one, we could bring a 9 out. All right, you always want to bring the coefficients out of these things. So then if we go to the table, see if I can get both our stuff on the same screen here. You just want to do the table for each of these individually. So our first one here is e to the negative 5t, which is the second row of the table, where our a is negative 5. So you just substitute in negative 5 in for the a, which we still have the 8 floating around, but then the the Laplace transform would be 1 over s plus 5. And then you can move the 8 back in if you really wanted to. So minus, then it's the Laplace transform of t cubed, which is the next one down. The n is 3, so that's going to be 3 factorial in the numerator, divided by s to the 3 plus 1 power. We'll clean that up in a minute. Plus 3 times the Laplace transform of t, which is the same row there. That's going to be a 1 factorial on top, and then an s to the 1 plus 1 power. And then minus 9 times the Laplace transform of 1, which is the first row there, 1 over s. Oh, oops. All right, then just clean it up. So bring all the constants back in. And that should be it. Just type it in just like that.
That's not bad.
Well, that's pretty easy when you have the table going.
I know. Oh my god. It is pretty.
They will probably also ask you for the restriction on S. So let's talk about that. Make sure we're right here. Okay, cool. Yeah, so then what is the restriction on S? And again, looking at the table, So when you have all of these combined together, you just want to take whatever the greatest restriction is. This first one, because the a is negative here for the e to the negative at, that's nothing. S greater than negative 5 is no different than s greater than 0, so we can ignore that one. For the second one, that was just s greater than 0, so that's not going to do anything for us. The t was also s greater than 0. The 1 was also s greater than 0. So it looks like of all of them combined, we're always just having s is greater than 0 as our restriction. Now, if any of these did have something like s is greater than 3, then that would need to be a 3 there.
Okay.
So it's just whatever the greatest restriction is.
It's not too bad.
Oh, and then there's these, right? So the piecewise stuff.
Oh, yeah.
Let's do one of these. So first off, it wants you to determine if it is continuous, piecewise continuous, or neither. And it also wants you to kind of sketch... Oh, maybe that's all they want you to do here. It's a good idea anyway, just to get these definitions down. So to determine if it's continuous or piecewise continuous, that all depends on what's happening at the transitions. So here at 3 and then at 7. If the values are equal, then it's continuous. If you have those jump discontinuities where it jumps either up or jumps down, that's when it's piecewise continuous. So let's just see what happens at those endpoints. So if I plug 3 into the first one, of course we're still just going to have 40. But if I plug 3 into the second one, 8 times 3 is something, 24. Minus 13 is 11. Which is definitely not equal to 40. So already it has to be piecewise continuous because we have a jump there at the 3. So it doesn't even really matter what happens at the 7. It's either going to be the same or it's going to jump, but we've already made a jump, so it has to be piecewise continuous. The only time it's going to be neither is if one of your functions is messed up. Like it has a t in the denominator, or it has a weird square root. One of the normal things that messes up. All right, and here I just want you to pick the right graph. Whichever one it is. I think it's A. Just looking at it, I think it's A.
Yeah.
I might be wrong.
Right.
Yeah, okay. All right, so that didn't actually have us finding the thing. It must have been earlier. I remember seeing one. Oh yeah, here we go. Okay, so finding the Laplace transform of this piecewise function, e to the 5t up to 1, and then just the constant 3 after that. Unfortunately, you cannot use the table for these piecewise ones. You have to use the integral formula.
Okay.
And then to do the integral formula, you're just splitting it up into the intervals. So we're going to have our first integral go from 0 to 1, and then it's going to be that e to the negative st times our function e to the 5t. And then that plus my second integral is just going from 1 to infinity. We still have the e to the negative st, and then that's going to be times 3. All right, then we have to do these. So our first integral from 0 to 1, we're going to do that same trick here that we did before. The e to the negative, and that's going to end up being s minus 5t. The second integral, there's not really much we can do there. I'll just leave it. I'll switch the places, but we'll leave it like that. So 3 e to the negative st. And then antiderivatives. So for this first one, again, we're bringing down that negative 1 over, for this example, s minus 5. And then we're also going to have the e just stuck there. All right, and then that one is going from 0 to 1. Plus, the other antiderivative is going to bring down a negative s. So we're going to have negative 3 over s e to the negative st. This one is going from 1 to infinity. All right, so does that make sense? Just doing the antiderivatives and then the limits? All right, so then just be careful plugging the stuff in. We're going to plug 1 in for the t value of this first one, which is going to give us a negative 1 over the s minus 5. And then if I plug 1 in for the t, I end up with e to the negative s minus 5. The t is now 1. And so it's going to be that minus plugging the 0 in for the t, which is going to make the e term go away, and we're going to end up with a negative 1 over s minus 5. All right, so that was just the first integral. Plus plugging infinity into the second integral, and again, plugging it into the t value. When I plug infinity in for this e, that e goes to the denominator and it blows up to infinity, so we just get 0. Minus, if I plug 1 in for the t, I'm going to end up with negative 3 over s and then e to the negative s. All right, now you just want to simplify it all down. All right, and then hopefully if you type it in, it'll say it works. So the Laplace transform of f of t is this. Oh, we do need the restriction. I'm pretty sure 5. Just because I see the s minus 5s in the denominator, so it has to be 5. Oh no. Did I mess up somewhere? Oh, I forgot my negative on the first one. So negative 1 over s minus 5. Okay, there we go. Yay. Yeah.
I feel like the hardest part is, for me, is plugging stuff in. Being like, oh yeah, it's still 0, but I feel like the more you do it, the better you get in it.
Right.
That wasn't that bad.
Do you want to look at some section 3 stuff?
Yeah, we can do that.
So this is kind of similar stuff. They give you a function, they give you the tables, and then they just ask you to find the transform. This first one should just be kind of direct, because you have an e to the at cosine bt, which is the first one. So you just write down the Laplace, plus e to the 5t, which is the second row here, and then minus 1, which is the first row. So you just, all together, just like the last section. Let's find a weird one, though. Here we go, a weird one. All right, so with this one, they also give you this table of properties, which is kind of nice. So, of course, adding functions together, we saw a constant. We've seen bringing out a constant. Multiplying by an e to the at out in front does something. And then the derivatives and raising stuff to powers, like all do something different. Somehow I lost my number here. There we go. So t plus 2 to the fourth. Let's look at that one. So we're trying to do the Laplace of t plus 2 to the fourth. Okay. All right, so t plus 2 to the fourth is not on the original table anywhere at all. But what this is it is a function that we can do to the n. Oh, no, sorry, those are derivatives. What am I thinking of? Oh, you know what we might have to do? I think we might just have to multiply that thing all out, unfortunately.
Oh, to the fourth. Okay. Yeah, no, it's not bad.
Let me just double check. Yeah, so I think you're just going to have to do that, because that's not quite any of the properties here with derivatives or constants or e to the at stuff. So you do have to multiply that one out. All right, I don't feel like doing this one anymore, but we'll skip to a better one. Same kind of thing. You'd have to actually FOIL this one out. Here we go. So one with a t out in front. Let's look at that. So t e to the 3t cosine of t. All right, looking at the properties, anytime that you have a t out in front here, this very last one, it's -1 to the n of whatever the power is on the t, and then whatever the derivative, so if it's a t to the 1, then first derivative, t squared, second derivative of the Laplace. So we could rewrite this. This is the same thing as -1, the derivative dds of the Laplace transform of just e to the 3t cosine t. So if you have a t inside the Laplace transform, then you could rewrite it as -1 times the derivative of the Laplace transform without the t. E to the 3t cosine t is one of the ones here at the bottom. So if my a is 3 and my b in this case is 1, this is going to be, we still have the -1 out in front. We still have the derivative dds. But now that Laplace transformation is going to be s minus a, which for us is s minus 3, divided by s minus 3 squared plus b, which is 1 squared. All right, and then unfortunately you're going to have to take the derivative of this, which is going to be a quotient rule thing. All right, so bottom times the derivative of the top minus the top times the derivative of the bottom, which is going to be a chain rule thing. And then that whole thing divided by the bottom squared. It didn't quite work out. There you go, that's better. So yeah, it's gross looking. We have the -1 out in front. Who's that came in? Barrick? Hey, Barrick. So bottom, derivative of the top, minus the top, derivative of the bottom, over the bottom squared. You could try cleaning this up if you want. I bet the homework would just take it.
I'll try cleaning it up and I'll end up messing it up.
I think I typed it in right. Oh no.
Not in the correct format.
Oh, I have an extra parentheses. That's why in the top. There he goes. See?
Oh, man.
Yeah, that's one nice thing about my math lab. You never have to simplify.
Good to know.
All right, but I hope the principle is okay and easy. So when you do have the
Right.
t, just take the derivative of the answer without the t, and then stick a negative in front.
And this one we're going backwards. We're going from the actual thing to the, I don't know what it's called.
Well, you're given the function,
Thing.
and you're trying to find the Laplace transform.
Okay.
It isn't until section 4 that you're doing it backwards, doing the inverse stuff. That's later.
Okay.
Barrick, do you have a specific question? We were just kind of going through the homeworks.
Be honest with you, I haven't done the homework yet.
Okay, well, we're just working through stuff if you want to work through stuff with us.
Sounds good.
All right.
Oh, what is that?
That one's bad.
You said,
One more reason to do it.
I think this one you have to get cute. Yeah, so with this one, you have to use a trig substitution.
joy.
Yeah, sine x times sine y. You would just have to look up on that trig identity sheet I gave you guys, but this is the substitution.
That doesn't look like anything on the trig I did.
I think it's one of like the last ones that we never use. The product to sum or sum to product, something like that. Let's see if we can just find it. Trig.
Wasn't that what I gave you just there?
It is, yeah, but that was gross looking. I was trying to find the sheet that I gave you guys. It should be on here somewhere. Maybe it's instead of trig substitution, trig identity. Yeah, this one. See, first one. There it is, down there at the bottom. Product identities. This one. Is this the sheet I gave you? No, it looks different. Sorry.
You gave us one similar to it.
Yeah, it looks close. Maybe it's still over here. That's still not it. This looks right.
Yeah, that one looks good.
Right off of Pinterest. So it's one of these bottom ones down here. We had sine alpha times sine beta, and it breaks down into this. 1/2 cosine alpha minus beta minus cosine alpha plus beta. All right, so going back to the homework question, when we have sine of 9t, sine of 3t, that would break down into 1/2 cosine of 9t minus 3t, which is 6t, and I think it was minus the two things added together, which was 12t. Did I do that right? 1/2 the minus minus the plus. Yeah, I like that. Okay, you'd have to distribute the 1/2 into here. So really what we're doing is the Laplace transform of 1/2 cosine 6t minus the Laplace transform 1/2 cosine 12t. All right, for both of these, we could take the 1/2 out. And then just looking up on that table of what the Laplace of cosine is, it's got to be one of the first ones, I'd imagine. No, it's way down here. Cosine of bt. So it's s over s squared plus the b squared. So we're going to have 1/2 cosine 6t is going to change into s over s squared plus 6 squared 36. Minus 1/2 of the cosine 12t, which is s over s squared plus 144. All right, and then I would probably just leave it like that.
Doesn't seem too bad.
Nope. Cool. So that's really, section 3 is really just continuing in section 2, just a little bit more difficult of problems where you have to think outside the box some. So let's see if there's anything else too crazy in here. Here's some more derivative stuff, but we've already kind of done derivative stuff with the t's out in front. This one seems complicated, but it's not complicated. Let's jump to the next one. Section 4. Section 4 is where you start doing it backwards. This is where you're given the Laplace transformation and you're trying to find the original function, the inverse Laplace transform. So let's see, just a quick example here. Like this, like if you're given this, 8 over s squared plus 49, when you go to the table, instead of looking at the first column, you want to look at the second column and see if you can find one that matches. Like this looks like the sine function. A constant on top, s squared plus a constant squared on the bottom. So just to kind of write it out, 8 over s squared plus 49. So what you want to do is you want to rearrange this so that it matches this perfectly. For it to match this perfectly, I would need a 7 in the numerator because the denominator has to be a 7 squared to make it a 49. So if b has to be a 7, I need to change this 8 into a 7. To change that 8 into a 7, we're going to take the 8 out. We're also going to take the reciprocal of 7 out and then plug it in. Like that. That way, if we did multiply the 8/7 back in, it would get me to the original thing. All right, so factor the 8 out, and then if I'm forcing a 7 to be in here, I have to also undo that by dividing by 7, just to make it equivalent. Now we can just write out the answer. Because if we're trying to take the inverse of this, the constant just stays in front, and then the inverse of a constant over s squared plus that constant squared is sine of that constant times t, just from the table. And that should be the answer.
Is there a reason you chose sine over cosine?
Because that was the one that matched. S is the variable,
okay.
So b is a
Yes,
constant.
yeah.
If this did have an s up top, I would have chose the cosine one. So just to make sure that we have the right answer here, 8/7 sine of 70. There we go. All right, so that's really all there is to this section, is you're just doing that process, but backwards. Some of them can get a little bit complicated, like this. This is where you'd have to do completing the square and or partial fractions.
And partial fractions?
Possibly partial fractions too, yeah. So if this bottom could be factored, then you would do partial fractions. But you would just have to play around with it.
Oh, I don't want to.
All right, let's do this one together, and then we'll probably get out of here because it's getting... Oh, we still got a few more minutes. Let's see how long this one takes, and we'll decide from there.
Okay.
All right, so just copying it down. All right, we're trying to take the inverse Laplace transform of this awful looking thing. There's definitely nothing on the table that matches this. So let's see if it can be factored. I kind of don't think so, because I don't know what goes into 52. Nothing, right?
4 does 13.
4 and 13. Yeah, but it still doesn't add to 12.
No.
So that's kind of it, right? Okay, so this
Yeah.
cannot be factored, and because it cannot be factored, so can't do partial fractions.
Good.
Yep. So then our only other step would have to be completing the square stuff. So let's try that. We're going to leave the numerator alone. But the denominator, we're going to do completing the square. So the first two terms we leave alone, and then you take half of the coefficient on S and then square it.
What is that?
Barrick, what are you doing?
I'm playing with a hard drive.
Oh.
So the S squared plus 12S, half of 12 is 6, squared is 36. But if you're going to add a 36 in the denominator, you also have to take it away. Still leaving... What's that?
Is there an equal sign in completing the square somewhere or no? Like, I thought you had to put it on the other side of the equal sign.
No, not like this. Sometimes yes, but we are not dealing with equations. We just have these expressions. So instead of putting it on the other side of the equal, we just put it with the opposite sign instead to cancel it out.
Okay, that's easier.
Mm-hmm. The reason we do this is because those first three terms will now factor into a perfect trinomial, S plus 6 squared. And then these last two things, 52 minus 36, I think that's 16.
52 minus 36. Yep, 16.
Okay, now let's go to our table and see if this matches anything even close over here. It's definitely none of the ones up top here. It has to be one of these three at the bottom just because we have the S plus or minus something in the denominator. It can't be this third from the bottom one because that does not have another little thing here. So it's going to have to be either one of these, and it may even be both. Just to kind of map out what I'm seeing, we have this S plus 6, which means that my A has to be negative 6. We have this plus 16, which says that my B has to be 4. So you want to look at the denominator to figure out the A and the B's. Now this does not help us out in the numerator though. So we're going to have to play around with the numerator until we can make it either be a B up top or an S minus A up top. And we may even need to split this up into two separate fractions to force it to be that way.
That makes sense.
So what I would do is because I have this 5 out in front here, and really it should be S minus A, I would factor a 5 out of this. So it's going to be 5 and then S plus. It would be really nice if I could make this to be an S plus 6 because they're supposed to match in the numerator and the denominator. So I'm just going to force it to be an S plus 6. So this is now 5 times 6 is 30. So of the 58 that we have up top, I've already used 30 of it, which means that there's 28 left over. All right, I know that was kind of weird, but if you multiply this out and combine it back together, you're going to end up here at the 5s plus 58. But we needed there to be an S plus 6 to match the S plus 6, since that's what the inverse trig needed. Still with me? Does that make sense? Okay. Now we're going to split this up into the two separate fractions. So we're going to have the first fraction be that first thing, the 5 times S plus 6 over the S plus 6 all squared plus 16. Plus the second fraction is just going to have that constant 28 up top, and then the s plus 6 all squared plus 16. This first term is going to be the e to the at cosine bt. The second term is going to be the e to the at sine bt. It's just that my b's don't quite match for either one yet. For the first one here, all I have to do is pull this 5 out, and remember you can pull constants out as much as you want, then that one matches perfectly now. This one, on the other hand, isn't quite going to match yet, so let's write some stuff down. So we had the 5 that we're pulling out. And then leaving this alone, so we're going to have s plus 6 up top, the s plus 6 squared plus 16 on the bottom. For the second one, I don't quite know what to do with the 28 yet, but I do know that it has to be a 4 up top, right? Because the b has to match the same b that's in the denominator. We have a 16 here, so that has to be the square root of 16 of 4. To factor out what we need to make that a 4, we have to factor out a 7. All right, now we're pretty much done. Because now it's going to be the 5 out in front, and then it's e to the a, which is negative 6t, cosine of 4t, plus 7, e to the at, sine of 4t. Just type it in, see if we got it right. Yay.
Interesting. That's very interesting.
So these can get a little bit hard with the completing the square and then with the partial fraction stuff, but just kind of follow the structure here, and it shouldn't be too bad in the end. Make sure you're following, or not following, make sure you have the table on hand so you can kind of see what your end goal needs to be for the different terms.
How's that partial fractions again? Like, as far as...
So if you had, let's see if I can find, like this. If you had one like this would be partial fraction stuff.
Oh yeah, I'm going to have to go back over that.
Mm-hmm. Or this one too. Partial fraction stuff. So like on this example here, you'd want to break this up to be a constant over the first term, plus a constant over the second one, plus a constant over the third one. Right, like that. Set that equal to this, and then figure out the 3 constants.
Oh my gosh, it all comes back. I remember doing that.
And then once you have the 3 constants, then you're just going to have a constant over s, which has to be this first one, and then a constant over s minus 4, which is the second one, constant over s minus 3, which is also the second one here. So once you actually do the partial fractions, it's not too bad. It's just finding the a, b, and c that can be annoying.
Okay. Yeah.
Okay.
All right.
Do you guys want to do a section 5 one? I've been kind of itching to do one.
Okay, we can do one.
Well, I mean, if you're itching for it, go right ahead.
Yeah, I haven't even got to that. Yeah.
That's all right. Well, it's just we've done everything we need to do to actually do the whole point of this, which is section 5. And they're real quick. So here we go. This is how you solve a differential equation using Laplace transforms. Here's our differential equation. So just copying it down, y double prime plus 3y prime plus 2y is equal to 168 e to the 5t. With initial conditions, y of 0 is negative 8. Y prime of 0 is 38. Okay, so what you want to do is you want to take the Laplace transformation of both sides. So we're going to do the Laplace transformation of y double prime plus the Laplace transformation of 3y prime plus the Laplace transformation of 2y. That's going to be equal to the Laplace transformation of 168 e to the 5t. All right, so just the Laplace transform of everything in the differential equation. Okay, then I would go over to scratch paper. And in scratch paper, I would figure out what these Laplace transforms are for each of the more difficult terms, like the derivative ones. So if we just go to our table of properties, one of the properties is derivatives. So here, this line, if I have the second derivative of the function, this is the formula. So we just copy down that formula. The second derivative is s squared, the Laplace transform of just the original function y, minus s times the original function y at 0, minus the derivative of the original function y at 0. And we know what these are because these are just the initial conditions that they give us. So s squared, the Laplace transform of y, we don't know what that is yet, minus s times the original function at 0, which is -8, minus the derivative of y at 0, which it tells us is 38. Okay, and then we can clean that up just like a little bit more. So that is s squared L of y plus 8s minus 38. Still in scratch paper, we would also want to figure out what the derivative of y is because of this 3y prime. That also has a formula to it over here. That's s, the Laplace transform of y, minus the function y at 0. Which again, we already know what that is because they give it to us. That's a -8, which the double negatives is going to make that a +8. Now that we've done all the scratch paper stuff, we can go back to our differential equation. First thing that we have is the Laplace of the second derivative, which we wrote down here. So that's going to be s squared, the Laplace of the function, plus 8s minus 38. That's going to be plus 3 times the Laplace of the first derivative, which is s Laplace of the function plus 8. That's going to be plus 2 times the Laplace of just the function y. That's going to be equal to, over here, the Laplace of 168 e to the 5t. We have to go back to the other table for that one. That's that second line here. E to the at changes into this. So the constant 168 just stays out in front. And then we're going to end up with 1 over s minus 5 for the Laplace transform. That's the e to the 5t changes into that. Okay, I know I went kind of quick there, but it's just using the properties and the formulas and plugging stuff in so that you change your differential equation into just Laplace of y's. Then you want to get everything that has a Laplace of y together. So all of the coefficients with an L, we have an s squared. We have a plus here, a plus 3s, and then here we have a plus 2. So all of that is multiplied on the Laplace of y. We do have some other stuff floating around that we can probably combine together. We have this plus 8s, which is doing nothing. We have a negative 38, and over here a plus 24, which is a negative 14. Then we still have the right-hand side. Moving all that other stuff over. So just subtracting the 8s and adding the 14. We are going to need this to all be one term over here. So we're going to have to do some like fraction stuff. Multiply top and bottom of these by s minus 5. That way, everything on the right-hand side has an s minus 5 in the denominator, and then we can just add all the numerators together to make it into a common fraction. So just trying to do all that. Here we have a negative 8s squared, so that's going to be out in front. Looks like we have a negative 40s and a plus 14s to be a negative 28s. And then I can't do the constants, but we have 168, and then we have whatever 14 times 5 is. I'll use my calculator real quick. Uh, 98. So we're just going to have a plus 98 on the end. That's going to be over just that s minus 5 for now. All right, last little part is we were trying to get that Laplace transform by itself. That's going to be dividing over that other awful looking thing. Okay, and then this was the stuff that we just saw in the last section. This is the Laplace transform of y, but we're going to want to find the inverse of that to get y itself. And y itself is the answer to the question. I don't know how difficult it's going to be to do this. I know it's partial fraction stuff, I can already tell, because you can factor that s squared plus 3s. Into s plus 2 and s plus 1. So then the partial fraction decomposition where every single one of these would get a constant up top. And then you'd have to figure out what those 3 constants are. I guess we could use that Symbolab and see if we can do it real quick.
Do you like Symbolab now?
It's like my new ... Will it do it with 3 different variables?
It should. Never tried it with 3. I've only done 2.
Partial fraction calculator. Symbolab. Okay.
So, yeah.
Example, partial fractions. All right, let's see if it does it. Okay, so we have, what do we have? Negative 8x squared plus, or no, minus 28s x plus 98. Okay, that all divided by, oh, jeez.
You have to highlight it and then do it.
Okay. All right, so that all divided by s minus 5, s plus 1, and s plus 2. Go. Oh, no, they're x's. Oh, no. Stop, Symbolab. I'm so sorry.
She didn't give it a heart attack like I did yesterday.
So let's see what it gives us here.
It basically just expanded the denominator.
Yeah, it didn't give us anything. Partial fraction. Oh, there it did it.
There you
Okay, cool. So for us, we have this. Get out of the way. All right, so we have negative 59 thirds, 1 over s plus 1, plus 122 sevenths, 1 over s plus 2, And then minus 121 over 21. And that's the 1 over s plus 5, s minus 5. Okay, and then each one of these is going to change into an e, right? Because each one of these is this second row here. So they're going to change into e and then the ATs with all these constants out in front. So negative 59 thirds. That's going to be e to the negative 1t. Plus 122 sevenths e to the negative 2t minus 121 over 21 e to the positive 5t. And then that's it. So that should be the answer. Oh, I didn't open this up in my teacher mode. Just quickly type it in. Oh no. Alright, so I think I just messed up some of my constants up top because I was doing stuff in my head. I should be pretty close though. Oh no, I was like way off. Well, anyway, you get the idea.
Yeah.
So I think where I had messed up was up here where I was combining like terms together, and I was trying to do all that math in my head, and I just messed it up. But this is the concept, right? So yeah, sorry I goofed it so bad. The answer is actually pretty nice.
And this little pause thing is just the same thing as we've been doing, just with the different method, I guess.
Yeah, it's solving the same equations that we have other ways to solve, but it's a lot quicker. Like notice that this could have fit into one page instead of the 3 pages it normally takes us to solve something like this.
Right.
Alright, but that's the idea of it. Even though I messed up some of my numbers somewhere.
So good.
Okay, cool. So I know that I like jumped way ahead all the way to section 5, but I hope it helps when you're working on your homework over the weekend.
Yeah, that's what I need. I have to get all caught up.
Okay.
Alright.
Alright.
Yeah, thanks for coming.
Thank you.
Yeah, I'll see you guys next week.